Welcome. So we're going to start talking about Cloud Native Buildpacks. So Cloud Native Buildpacks are the magic which turn your code into something that runs and powers Salesforce functions. But first, who we are. I'm Andre, Director of Product Management for the languages team. We've got Manuel, who owns our JVM frameworks and the JVM languages on our platform. And we've got Terrence, who is the architect for builds and languages. But now the slide you've all been waiting for, the forward-looking statements. So please make all purchasing decisions based upon publicly available and generally available information. We will be making some mention about future plans in this talk, so please take this to heart. So a brief overview of what we're going to chat about. First, our philosophy as we were building Salesforce functions. We are built on open standards. We're going to chat a little bit about Cloud Native Buildpacks themselves, provide you an overview of what they are, how you're going to use them. And we're going to go into a very technical deep dive about Cloud Native Buildpacks, how to build them. And we'll chat a little bit about building CNBs as a platform. So Salesforce Functions is a platform built upon open standards. Let's chat about this philosophy just a little bit. So Salesforce Functions lets you extend the Salesforce platform with code written in the languages you already know and love, whether or not that's Java, JavaScript, TypeScript, and we're working on Python. However, the fun doesn't just stop there. We're also working on a way for you to bring your own languages using Cloud Native Buildpacks to Salesforce Functions. So for any of you Haskell developers, which may be in the audience, we see you. You have the power. However, it's more than just the language. It's the entire ecosystem. By leveraging the millions upon millions of packages available to you in NPM, or Maven Central, or your favorite package manager in any other ecosystem, Salesforce Functions gives you access to the entirety of these ecosystems, all of these tools, whether or not it's a library to create PDFs, your favorite machine learning library, or that new testing framework that you saw in Hacker News this morning. Continuing with our adoption of open standards, they're not specific to the languages used, but also how we build Salesforce Functions itself. We build on open standards throughout the entire stack. All of our build packs are open source, publicly available. You can play with them, break them, so on and so forth. So behind the scenes, and Manuel will talk about this more, we turn your code into an open container image. Really, it's just a Docker container, except it's non-proprietary. And we do this via Cloud Native Buildpacks. So Cloud Native Buildpacks, CNBs, are a CNCF project, a Cloud Native Computing Foundation project. And the CNCF is home to projects like Kubernetes, gRPC, among others. And we are proud to sit along with these other projects as an open standard. At their core, Buildpacks turn your source code into a container image. We're going to go into a little bit more detail in just a moment, and Manuel will kick that off on how we use Buildpacks within Salesforce Functions.
Thanks, Andre. So before we can start, we actually need to know what needs to go in one of these images, right? So first, every function container needs to expose a standardized HTTP interface that we use to invoke your function. And for this, we develop what we call function runtimes. These are open source, and these runtimes wrap your source code and expose the required interface. Next, usually these runtimes are written in the language they support. So that means for a Java example, we would need to install a Java runtime environment like OpenJDK. And the final piece is the customer's function itself. Besides getting the source, we actually need to build your function, download the dependencies your function have, and we might even need to execute additional build steps like code generation. We support industry standard tools for these tasks. For Java, this means Maven. And for Node, we support NPM. Let's talk about the build packs that perform these necessary steps to build your container. The OpenJDK build pack pretty obviously installs OpenJDK. It does that by first determining which OpenJDK version needs to be installed. And as a customer, you can just specify any version you like. But we recommend that you only specify a major version, and the build pack will then automatically pick up the most recent release for that major version. And that's the main value this build pack provides. It's not the code, it's that we maintain it, and we have always the most recent and most secure version of OpenJDK in this case available for you. The main purpose of the Maven build pack is to run Maven and compile your application or function. We use some opinionated defaults, like which Maven goals we want to execute or how Maven is configured. But customers can fully configure the goals and the configuration options if they like. We also had some additional configuration that is not overridable that we use to make sure that Maven writes the downloaded dependencies to a folder that is cached between builds, so you don't have to re-download your dependencies every time. But to run Maven, we actually need Maven, right? So that build pack installs Maven for you. But it will not be part of the resulting image. At runtime, you don't need Maven anymore, right? So this is an example of a build pack providing build tooling to other build packs and itself. However, we encourage customers to not rely on a Maven version we just install. If you have a Maven wrapper in your function, we will use that wrapper instead to make sure you have that nice dev prod parity that you want. Besides downloading the Java function runtime, this build pack will actually execute the Java function runtime at build to verify that the function you are trying to build is actually runnable. In the case of a Java function, the inputs and outputs of a function need to be serializable from and to JSON, and you can provide your own deserialize and serialize if you want, but we also provide some standard ones. So that build pack will run this validation, look at your class files, introspect the bytecode, and see these are the types that you declared, and then fails the build early if there is no JSON serialization available for you. This gives a nice, faster feedback cycle for your developers. OK, this is a visual representation of what we've talked about so far. You can see all the build packs and how they depend on each other. But how do we determine which build packs actually need to run? You see here we have Java and NPM. And this is the job of the CNB detect phase. And in this phase, every build pack is asked, can you handle this application code? In the case of Salesforce function, this means your actual function code that you wrote. OK, let's say we have a Salesforce function written in Java. What would happen during this detect phase? For the Maven build pack, this is very simple. Maven projects contain a pom.xml file that configures your dependencies, your build steps, all that jazz. And that build pack will simply look, does this application have a pom.xml file checked in? And if it does, it will say, yes, I can handle this. Something similar happens with the Java function runtime build pack. We have a file called project.toml that contains, among other things, metadata about your function. And we just assume that your application is a function if it has this file. The OpenJDK build pack, however, behaves a little counterintuitive at first, because it will always fail detection. We do that to separate concerns between build packs as much as we can. Imagine we would check for a pom.xml file in OpenJDK and then assume, oh, that must be a Java application. That only works if we only support Maven. But let's say we add another build pack into the mix, like build tool into the mix, like Gradle. Then pom.xml is no longer a great indicator for a Java app. So how is this going to work then? We clearly need OpenJDK for Maven and the function runtime and your function. So in addition to just signaling true false, I can handle this application source or not. Build packs can write a file that specifies dependencies on other build packs and the dependencies they provide for others. So as you can see here, the OpenJDK build pack says, I provide OpenJDK. And Maven and the Java function runtime say, I need OpenJDK. So even though the detect initially failed, the CNB runtime will mark this as a participating build pack because it provides a necessary dependency for the other build packs. In fact, there are more provide require pairs here. The Java function runtime requires compiled class files to be able to run. This is what the Maven buildpack outputs. And as I mentioned earlier, the function runtime buildpack just looks for that project.toml file. And the Node version of the same buildpack does the same thing. They're identical. If we wouldn't check for these class files, we could by accident, run the Node function runtime, which wouldn't work for a Java function, of course. And as you can imagine, the Node ones will just fail. There's no package.json, nor is there a requirement to have transpile TypeScript and stuff. What's cool about buildpacks is that they're ordinary executables. They're not lists of shell commands that need to be run, like in a Docker file. So this allows us to keep context between external commands that we execute and allows us to map exit codes or even output on standard error to make like nice, understandable error messages with a clear call to action that help you fix potential problems with your function. One thing I did mention before, that most of these buildpacks are not even Salesforce function specific. The only specific buildpack is the function runtime buildpack, and we can reuse the OpenJDK or the Maven buildpack in different contexts, and we do that. This ensures we have a consistent and great developer experience across products. And it also makes my job easier because I have to only maintain one OpenJDK buildpack and not 10 of them. The buildpack spec is low level, so this allows us to implement buildpacks in almost any language. We choose to write our buildpacks in Rust. We value the strong guarantees that the language gives us with all the error states a buildpack could potentially be in. Historically, at Heroku, all our buildpacks were written in Bash, and now with Rust, we are able to easily share components between buildpacks across languages, so we have a consistent and nice developer experience. We wrote a framework for that to make implementing buildpacks in Rust easy and efficient. It has testing capabilities that allow you to run your buildpack locally, and it has been an open source project right from the start. And if you're interested in how things work under the hood, you can take a look at the repository, and we will have a QR code at the end of the presentation that you can snap a picture of and look at it later. And I will now hand it off to Terrence.
Thanks, Manuel. So now that we've looked at how Salesforce leverages and uses buildpacks for building Salesforce functions, I wanted to kind of take a step back and look at buildpacks kind of as a platform and some of the benefits of using kind of open standards and open source technologies and some of the things that you get along for kind of going on that path. So, one of the things that Manuel touched on was kind of that the tech graph where we talked about being able to have these like composable units and these kind of individual build packs that can be kind of inserted as part of this build pipeline. So you're able to have these kind of distinct pieces when you kind of went over all those different paths. But going kind of through that node example, what happens if we, so right now in Salesforce Functions, we support NPM as kind of the dependency manager. What if your project or function used Yarn? Like how hard would that be to actually add into this build pipeline? So you could probably leverage, in fact, almost all of the existing Salesforce build packs that we're providing, and then just write this single Yarn build pack that you would then fit using kind of the build and requires that Manuel talked about. So it would require that there is a Node engine that's installed, and then it goes through and kind of installs those dependencies. And so you can edit this build pipeline, and it's very kind of malleable and composable as discrete units that you can think of. But then, Andre talked about wanting to potentially add in Haskell. Like maybe you want to write Salesforce functions or something that support an entire language that we don't support at all. And so what does that look like? You basically could take a look at all the build packs we have that are open source that Manuel talked about and basically recreate an entire build pipeline that work just like our build packs do to basically build those container images that would run on our platform. In addition to that, as part of the Cloud Native Buildpacks project, there's actually a tool that is provided called Pack, which is a local CLI that allows you to essentially like build container images locally, as well as once you've had those images, you can actually go ahead and run them. And so one of the things that we actually do as part of the Salesforce Functions, we provide what we call builder images, which are a thing that's part of the Cloud Native Buildpacks project. And all it is actually a container image that has all the build packs that you want to run on top of an existing stack. So we provide basically a stack that is done by Heroku that contains all this stuff, and they're all public. You can download them off of Docker Hub, and the source code's actually all available. And so using that builder, you can actually go ahead and build a Salesforce function that's the same that you would do if you push that code up to our platform when we built it. So you're able to basically have this local development experience that is very close to production, build that container image, and actually run that locally, which is really cool. And one of the other things that has actually been a big focus of the Cloud Native Buildpacks project has been basically building this like build provenance of what is actually in this container image that we're constructing for you. So as part of the project, we've been doing stuff around software bill of materials where we kind of standardize where that should be put, and then giving Buildpack authors the basically tooling to essentially put this in your container image so you can know what's actually in there. So when you go ahead and install your JDK, you want to know what version that's in there, the license of that, the checksum, like where you got that, where that lives. And so when you go and inspect this image later, you know what's there. So you can see that not only from the open JDK, like actually all the dependencies that Maven's installing, and potentially all the build packs actually involved in this process to actually get you that image. So given a machine-readable file, you can actually essentially see what you're actually running in production for every single kind of container image that you're getting through Cloud Native Buildpacks. So kind of just some of the things that are part of the kind of upstream project that are cool and that we're looking at. So in conclusion, Salesforce Function is a platform for open standards, all the way from the languages that are available to you to use for Salesforce Functions. The function runtimes are open source that we actually use to actually run your function in Salesforce Functions. Manuel talked about libcmbrs, the kind of framework that we have written in Rust to actually write our build packs that you're able to use, and you can kind of go there and see that. The actual artifacts, those images, are part of an open standard as part of the Open Container Initiative, and even the build packs themselves, right? The project, the build pipeline, and then our build packs themselves are all open source. So the entire stack kind of being built on top of open standards here. And if you're interested in learning more about Cloud Native Buildpacks, you can head over to Buildpacks.io. Here's the QR code, and that's for the Cloud Native Buildpacks project. If you're interested in learning more about that Buildpack framework written in Rust that we use in-house at Salesforce, you can go over here on GitHub and scan that QR code to kind of get that. And that's all I had. So thank you, and please fill out your session surveys.